Good evening, everyone. Our paper today is LLMs Get Lost in Multi-Turn Conversations, published at ICLR 2026 by Lab Hayashi, Zhu, and Neville from Microsoft Research and Salesforce Research. I'm Rania, presenting alongside Bhargav and Manish for Computer Science 3793. So, what is this paper actually about? Think about the last time you used ChatGPT or Claude. Did you type out one perfectly written paragraph with every single detail spelled out? Probably not. Most people type something vague like write me this function or like follow up with, oh, it should be handled by edge cases and then actually make it return a sorted list or something like that. So that's the left side of the slide, how LLMs are actually used. Short messages, gradual reveal, and messy and incremental. But the right side of this shows how LLMs are evaluated. Benchmarks like Human Eval and GSM-8K assume that user sends one perfectly written, fully specified instruction and the model answers. Clean, unambiguous. The paper's central observation is simple but powerful. There is a massive gap between how we test LLMs and how people actually talk to them, and nobody had measured how big that gap was until this paper. So, how did the prior work try to address this? There were three main approaches, and each one has a critical blind spot. First, single turn benchmarks, things like Human Evolve and Spider. These are the gold standard in the field, but they all assume that the user can perfectly articulate everything in one message upfront. But that's not realistic. Second, episodic multi-turn benchmarks like MT-bench, MT-eval, these do use multiple turns, but here's the key problem. Each turn is a completely independent subtask graded on its own. So that is a fundamentally different from a user gradually revealing one complex requirement. It doesn't simulate underspecification at all. Third, system prompt engineering. Some researchers tried just telling the model, hey, the user might not give you all the information at once, but we'll see this later that it had no effects at all. So prior work was either ignoring multi-turn entirely or testing a version of multi-turn that doesn't reflect how people actually communicate. Which brings us to why none of that was good enough. And this slide captures the three core gaps that this paper fills. Gap 1: episodic is not the same as underspecified. Prior benchmarks treat each turn as its own mini task, but in real conversation, there's one goal being built up gradually. The model has to hold an incomplete picture in mind and keep updating it. So there's a totally different cognitive challenge, and there's no benchmark that had studied it at scale. Gap 2: no apples to apples comparison because prior work never ran the same instruction in both single turn and multi turn modes. It was impossible to actually measure the performance drop. You couldn't isolate the effect of multi turn under specification. This paper does that by design. Gap 3: underspecification is extremely common but was being ignored. Studies of real users' logs confirm that incomplete instructions are the norm, not the exception. People naturally reveal information gradually. There's even a principle from linguistics called principle of least effort. Humans don't overspecify when they don't have to. This paper is the first large-scale controlled study directly comparing the same LLM tasks in single-turn versus multi-turn under specified settings, and what they found was alarming, which Manish will now walk through.
Thank you, Rania. I'll be covering the paper's core findings and how the experiments were designed. Let's start with the headline number, minus 39%. Across all 15 LLMs tested, performance dropped an average of 39% when moving from single-turn fully specified conversations to multi-turn underspecified ones on the exact same task. And three things make this especially striking. First, it happens to every single model, from the small open source Llama 3.18b all the way up to Gemini 2.5 Pro and GPT 4.1 second. It appears in conversations as short as 2 turns. There's no safe minimum. Third, the state of the art is not immune. Bigger, smarter models drop just as much as in percentage terms as the weaker ones. The authors named this as the lost in conversation phenomenon. Once a model takes a wrong turn, it does not recover. Now, here's the paper's most important analytical insight, and it changes how we should think about LLM evaluation entirely. The authors separate two different dimensions of model quality: aptitude, the 90th percentile score, meaning best case performance, and the unreliability, the gap between the 90th and the 10th percentile, meaning how inconsistent the model is across identical runs. In single turn settings, these track these track together. Better models are more reliable. High aptitude predicts low variance. That's what we've always assumed. In multi-turn settings, that relationship breaks completely. Aptitude only drops 16%. Models mostly still know how to do tasks in their best runs, but unreliability more than doubles plus 112%. The performance collapse is not because of models forgot how to solve problems. It's because they became wildly inconsistent. The same instructions might succeed once and fail 5 times. And no model, no matter how capable, is immune to this. So why does this happen? The authors propose four behavioral causes, and they empirically validate every one of them. Cause one: premature answer attempts. Models try to give a full answer before all requirements are known. The early wrong assumptions get baked into the solution and are never corrected. Cause two: answer bloat. Instead of revising answers when new information comes in, models append to what they were already given or wrote. Solutions grow to 20 to 300% longer and carry all prior mistakes forward. Cause three: loss in middle turns. Models overweigh information from the first and the last turns of conversation. Requirements introduced in the middle get symmetrically forgotten. A recency primacy bias. Cause four: over-verbosity. Longer responses introduce more unstated assumptions. On 5 of the 6 tasks, the shortest response quintile outperforms the longest by 10 to 50%. Each of these causes is validated with its own experiment, which I'll explain now through the experimental design. The overall experimental design is elegant. Take 600 high-quality single-turn instructions across 6 tasks. Apply a sharding process to split each instruction into 3 to 8 natural sub-requirements. Simulate 5 different conversation types. Run 10 simulations per model instruction type combination across 15 LLMs. Score everything. So total over 200,000 simulated conversations at a cost of roughly 5,000 in API compute. 5 conversation formats were tested. Full is the baseline, full instruction in 1 turn. Concat paste all the shards as bullet list in 1 turn. Same content, controls for rephrasing. Sharded is the core condition, one requirement per turn. The model never sees the full picture. Recap adds a final turn, restating everything. Snowball repeats all prior shards every turn. The critical comparison is always full versus sharded. Six tasks cover both programming and language: code, database, actions, math, data to text, and summarization. Each uses its original benchmark metric. Sharding is a four-step process: segment the instruction, rephrase each piece conversationally, verify no information was lost, then manually inspect every result. Every sharded instruction was a human-reviewed process. Each conversation uses three automated components: a user simulator that reveals one shard per turn, the evaluated assistant which never knows it's being tested, and a strategy classifier plus an answer extractor which scores each response. Final score equals the best attempt across all turns. Manual review confirmed 97% pipeline accuracy. So now over to Bargo for the results.
Let's get into results. The headline is confirmed at scale. Every one of the 15 models tested shows statistically significant degradation in the sharded condition. The average drop is 39%. Critically, Concat recovers about 95% of full performance. That's the control condition. The rules of rephrasing as the cause. The information content is identical between Concat and sharded. Only the delivery mode differs, so we know for certain it is the multi-turn under specification structure itself that causes the collapse, not anything about how the shards were written. And larger, more capable models, GPT 4.1, Gemini 2.5 Pro, Claude 3.7 Sonnet, degrade just as much as smaller models. Scale is not a solution. This is the result that should change how the field evaluates models. Aptitude drops only 16% in their best runs. Models mostly still succeed, but unreliability surges 112%. The same instruction that a model solves correctly in one run will fail in multiple others, not because the model lost capability, but because the conversation introduced structural instability. In singleton settings, better models are more reliable. Aptitude predicts consistency. In multi-turn settings, all models converge to the same high unreliability, regardless of how strong they are. Aptitude no longer predicts anything. A model that's right 90% of the time in a lab setting might succeed only 50% of the time or less when a real user types incrementally. Each of the four behavioral root causes the authors hypothesized is validated experimentally. Cause 1: premature answers. Models that make their first answer attempt in the earliest 20% of a conversation score about 31 on average. Models that wait until 80 to 100% of requirements are reveal score 64, nearly double. That pattern holds across all 15 models. Waiting works. Cause 2: answer bloat. In sharded conversations, answer length grows from roughly 700 characters at attempt 1 to over 1400 characters by attempt 10. Even when models reach a correct answer is sharded, the solution is 27% longer for code and 14% longer for SQL than the full equivalent, bloated with prior wrong assumptions. Cause 3: loss in middle turns. A citation heat map from the summarization task shows 20 to 30% citation coverage for documents from the first and last attempts, but only 8 to 13% for middle turns. Middle turn requirements are systematically neglected. Cause 4: over-verbosity. On 5 of 6 tasks, the shortest response quintile outperforms the longest by 10 to 50%. Concise turns keep the conversation on track, verbose turns derail it. The natural question is, can we fix this with workarounds? The authors tested three agent-style approaches: recap and snowball. Snowball, which repeats all prior shards every turn, recovers about 15 to 20% of that degradation. That's meaningful, but still leaves a large gap. Recap is even more effective, but it requires knowing when the conversation ends, which is unrealistic in a real deployment. Lowering temperature to zero. In singleton settings, this helps a lot, 50 to 80% reliability improvement. In multi-turn settings, almost nothing. Even at t=0, unreliability remains around 30%. Why? Because one early random token in turn 2 cascades into divergent paths for the entire rest of the conversation. Determinism can't prevent that. System prompt hint. Adding a sentence telling the model the user might be underspecified yields plus 1% on average, with individual tasks going up 7 points and one going down 6. The verdict: none of these close the gap. You cannot patch multi-turn unreliability with inference time tricks. The gradual sharding experiment answers a precise question: exactly how many turns does it take for models to get lost? The answer is two. Going from one shard single turn to two shards, just one follow-up, is where unreliability makes its biggest single jump. For both GPT-4o and GPT-4o Mini, the pattern is identical. Aptitude stays relatively flat, but unreliability spikes sharply at the two-shard mark and then levels off. This rules out context length as the cause. The problem isn't that the context gets long, it's that the structural shift from single-turn to multi-turn itself is the causal factor. There is no short enough conversation that avoids the problem. If there's more than one turn, you're at risk. The paper closes with four directions for future work. First, creative tasks. This paper only tested analytical domains. Do LLMs get lost in multi-turn creative writing? Unknown. Second, other languages. Everything here was English. Multilingual degradation is an open question. Third, multimodal conversations. What happens when users share images or documents across turns instead of text? Likely worse. Fourth, better training objectives. The authors call on LLM builders to explicitly optimize for multi-turn reliability, targeting unreliability below 15 at default temperature. The paper will publicly release all sharded instructions and simulation code to enable follow-up work. 5 takeaways to close. 1. The 39% drop is universal. Scale doesn't protect you. 2. The cause is unreliability, not inability. Altitude drops 16%, unreliability doubles. 3. 4 behavioral roots causes. Premature answers, bloat, forgetting middle turns, over verbosity, all empirically validated. 4. Workarounds don't solve it. Agent frameworks, temperature prompts, all marginal. 5. Multi-turn reliability must become a first-class training objective. Single-turn benchmarks systematically overestimate real-world LLM capability. To quote the paper directly, if an LLM takes a wrong turn in conversation, it gets lost and does not recover. Thank you. We're happy to take any questions.